let's talk about what we're going to talk about today. I want to talk about the Ruby Sims. And notice this is part 2 of a talk that actually has like 10 parts, but I don't want to bore you guys for hours and hours and hours, so we're just going to get on with part 2. So let's talk about what we're going to talk about today. I'm Bryan on Twitter, and that's really all you need to know about me, but we're going to talk about other things today. We're actually here to talk about simulations. And our simulation is we're going to talk about interactions of a group of people, this group of people, over time. And what we're going to talk about is this blonde girl gets with this black guy. This black guy gets with this girl in the purple sweater. This girl in the purple sweater gets with this guy, I don't know his name, let's call him Vincent. And Vincent likes Paul. So why are we doing this? Well, the reason we're doing this is because we want to talk about a cootie simulator. So really what we're going to do today is we're going to model cooties in a large population. So look around, look left, look right. I'm actually talking about you guys giving cooties to each other. So before we get started, normally people who do simulations like this, they don't use Ruby. And they don't use Ruby because Ruby is just not really an accepted scientific language. People are not doing great things in science. But you know something? I like Ruby, you guys like Ruby, so let's try Ruby. So let's talk about this simulation. Before we get out of the way, there's 2 types of simulations that we can create. We can create a stochastic simulation and we can create a deterministic. These are very big words. You can look them up on Wikipedia later, but the interesting way of thinking about it is stochastic means there's a RAND involved, deterministic means there's no RAND involved. Usually with deterministic simulations, they are modeled in like MATLAB or Mathematica or Octave, and it's just a whole long list of differential equations. But you know what? I'm not that smart, so we're going to do it the old-fashioned way. We're just going to use RAND. And in our simulation, simulations are actually very simple. Usually for a simulation, you need to define some input, you need to compute, and you need to analyze the output. It's kind of like OO. This is why I think that doing simulations in Ruby is, or could be, a great fit. So let's get into some code. So when I started writing a simulation, I wrote no test, because you know what? I didn't even know what I was doing, so I spiked out some things. So I realized that what I wanted to do is I wanted to create people, and then I wanted a report method, and I wanted a way to simulate or run a simulation loop, and I just wrote a little bit of code that actually does this. And you'll notice that in my simulate 2, it takes a block, and it's not important what's in there, but all it does is it mishes and matches people. So really, it just simulates you touching the person to your left or your right. So how do we write a simulator? Well, first thing we need to do is we need to define inputs. Very simple. Just look at this code. It's very easy to understand. This is one of the reasons why I wanted to choose Ruby, because writing this in some other crazy language would not be as easy to explain to a group of people who have no idea what I'm talking about. So next thing you want to do is compute. And in our compute, all we do is create pairs. So look to the left, look to the right, touch that person, that's your pair. And then you're going to transmit however you want to transmit your cooties. And then we're going to say that people who already have cooties, we want to see if their cooties turns into cootiosis, because you know that is a big deal. So after we go through all of our iterations of our simulation, so you touch the person in front of you, touch the person in the back of you, you ran to the front of the room, you ran to the back of the room. We just want to analyze our output, because that's how scientists work. They perform a hypothesis, they do experiments, they analyze results, because we're all scientists now. So, real quick here, can I have some sound? Or maybe, yes, I have sound.
I didn't trust him. I didn't know I could catch it on the playground.
We were in love, so I didn't think about it.
All I did is trade Lunchables.
Every year, 2 million kids are infected with cooties.
Why didn't you tell me, baby?
I thought cooties was something that happened to other kids.
Cody! I just wanted to play tag. I never thought I'd be it.
And the numbers are growing.
I blame myself.
I made a big mistake.
And even though a vaccine is available,
Circle, circle, dot, dot, now you're at the cootie shop.
most children never get inoculated.
You may have of cooties. And not even know it. I wish someone had told me.
Speak to your kids about cooties before cooties speaks to them first.
What do I do now?
So now, after that little short video, you know why this research into actually solving the problem, which is cooties, is so important. So, let me explain to you how we're trying to do this. So, when we actually have our cootie simulator, there's a loop, and we loop on days. And so let's talk about what's in a day. In a day, we create a new pair. And because I love to show code in my slides, I'm just going to do that for a while. Hopefully you guys can follow along. So we have create pairs. So what we do is we take everybody who's not in a pair, and we add them to a pair. And we use some cool little things in Ruby, like the shuffle command that you can do. And then we take each slice, which you can get from enumerable, and then we map that. This is one of the real reasons why we love Ruby for these types of simulations. Notice that this code right here is only Ruby 1.9 compatible. Don't run this in 1.8. You couldn't copy and paste this because I like the dots to be on the beginning of the line rather than at the end of the line. And the next thing we do is we transmit cooties. And once again, this is a very, very simple calculation. So what we do now is when we say we want to transmit, we just go to each person. I call them alpha and beta in a pair because I can't think of a better name. And I just say, hey, you transmit this way, and hey, you transmit that way. And if someone has something, they share. And the next thing we do is we track progress for the infection. And very simple once again. And the whole point of this type of writing these simulations in Ruby is that this is very readable. Someone who didn't even really know Ruby could almost understand what's going on here. But unfortunately, there is a big caveat of Ruby. Ruby isn't fast. Matter of fact, take a little sidebar here. Ruby is actually pretty great in web world. I'm sure a lot of you here have made very, very fast web applications in Ruby. But the way that you've done that is you've done it by not doing something. You've either cached or you've optimized to not run. And I'll show you. This cootie simulation, whenever I run it for 100 people, or the original version for 100 people over 1 year, it took 28 seconds. And I said, that's nearly not going to cut it because you know what, a 1 year, 100-person simulation is just not really worth it. We really want to do 100 year, 1 million people. So I did the math and I realized this is not going to work. So let's talk about why it's not going to work. Well, here, this right here is output from RubyProf. And you'll notice that most of the time is spent in array each, but if you look below that, these next 3 lines is really where we're spending a lot of the time. And what's happening here is we are trying to compare 2 dates. So each time that we need to go through the iteration, we need to figure out if pairs are active and if they're actually valid, and we have to compare them against each other. We have to compare dates against each other. And the problem is that this, unfortunately, in Ruby, out of the box, this set of things are very, very slow. So I thought about it. So let me get crazy here. So I said, why don't I just override enumerable? What wrong can come out of overriding enumerable? So I said, let me come up with this concept called a parallel each. So what I'll do is I'll have a regular each, and you'll have a block to it, and I'll just basically create a thread, I'll yield, and then I'll have my cleanup, and I'll go ahead. Don't do this. I'll solve a lot of problems for you right now. This is not a solution for pretty much any problem you're going to have. So here's another graph, and this graph right here is from perftools.rb, running on Google Perf Tools. And I got to flip up my iPad because I can't see. So what this is really showing is that this is actually with RubyProf, what we're actually seeing is we're seeing a profiler. With Perf Tools, it's actually a sampler. It says at predefined intervals, this is what's happening. And Perf Tools is still finding that, hey, I'm trying to find all my people. It's taking forever. So let's go into this a little bit. So we have 100 people. We have and let's say if we do 3,650 iterations, which would be 10 years, we could potentially have 365,000 actions. So if we look at this and we actually think about how many actions we're going to have for like 1 million people, that's a really large number. And I think that's hundreds, millions, billions, 3 billion actions. That's just a lot. So how do we make this faster? Well, the first thing I would think is, hey, let's get a faster CPU. But the problem is that we're really not making faster CPUs anymore. I mean, we just realized that making faster CPUs is not the way to solve all these big issues. So let's approach this a little bit differently. So there's 2 things we can do. We can run less code, or we can do more things at once. But really, we can't make it faster. So before we go into that, let's talk about Ruby. So in 1.9, if Ruby 1.9 runs things sequentially. Basically, you have one instruction, second instruction, third instruction. So you can get fancy and say, hey, I'm going to throw up a new thread. But here's the problem in Ruby 1.9, or MRI. So pretend that this box models your CPU that has 4 cores. Even if you do thread new in Ruby 1.9, you're only going to be on 1 CPU. The green threads only limits you to 1 CPU. So you could do a whole bunch of things on your 1 CPU. So let's bring JRuby into the equation. Anyone here use JRuby? Anyone here like JRuby? I like JRuby. So let's look at this again for JRuby. Look, you have statement 1, statement 2, statement 3. You run thread new. Hey, look, you're on all the cores. That's a big improvement. And also, another thing to think about is JRuby has Hotspot. Hotspot is really their gift to the world. Hotspot is very, very amazing, and I'll show you some slides in a little while that actually show you how amazing Hotspot is. So what I did for this simulator is I changed 1 line of code, and I ran the same exact code in JRuby. Look at this speed up. We went from 28 seconds down to 10 seconds. It's like, wow, JRuby is awesome. But we'll come back to that later. So here's one thing. I love JRuby, and JRuby is awesome, but I'm what I would call a TDDist. I write my tests first, generally, and then I write code, and then I check for things, and then I repeat the process. The problem with JRuby is that you can't have a very fast process for doing that in JRuby. There's just no way, because if you have to spin up a new JRuby interpreter, it's just very, very slow, and it really does interrupt your flow. So I was thinking, well, I just want to code using 193 and MRI, so I need to figure out a way to do more than one things with MRI. So I said, well, I could fork. If you fork in MRI, you will be on another CPU, most likely, or another core. Or I said, but you know what? Forking code just gets me into another world of problems that I really don't want to have. So what I was thinking, well, maybe I could do external processes. Maybe I could use something like rescue. Maybe I could use something like sidekick, or I could go out to 0MQ and have something listening on sockets. I don't know. So, but I actually have a way better solution than that for all this, and so let's move on to statistics. Anyone here good at statistics? I'm going to give you a primer on statistics because I want to throw as many things at you as one talk as I can. So there's 5 words up here. There's mean, median, variance, standard deviation. And that little symbol right there stands for standard deviation. That's all you need to know about statistics. So why would we use statistics? Here's a good one. How do I randomly pick an integer from 1 to 6? Were you thinking something like this, everybody in the crowd? Hopefully you guys are thinking something like this. Anyone thinking something different? Well, I have a different solution for you. So as part of this process, we wrote this gem called VOS. And what VOS is an implementation of the VOS alias method. And what the VOS alias method is a way of sampling a discrete probability in constant time. Well, what does that mean? So more code for you. So let's say we instantiate our VOS alias method. And what we're doing right here is we're basically saying we have a die, and I roll it. And each side has equal probability of coming up, and I roll it. and I roll it, and I roll it, and I do that 9,997 more times, what happens? That's what the Fuselius method allows me to do. It allows me to say that I have a discrete probability, and I want to sample the next choice. But you know what? It's actually shorter to do this in rand. But what if the die is weighted? What if the 1 comes up 1.2 times more than any other number? Because, if I'm playing craps with you, I'm not using a fair die. So the problem here is that you can't use rand anymore. So that's what we use. We use this Fuselius method, and we sample that, and what will happen here is that choice number 1 in this array will actually come up 1.2 times more than any other choice. But why is this important? So let's say we have this mountain, and let's just call this mountain a probability distribution function, or a PDF. You guys might recognize this as a bell curve. This is probably how you got your B's and C's in college. So let's say a good example of this would be that, towards the middle, A's, B's, and C's. We have to have, someone in a class has to get an A. So what we'll do is we'll fit this curve so someone in the class gets the A's, and then the majority of people get C's. So we have this PDF function. But there's also something called a CDF, or a cumulative distribution function. And it's actually modeled from a PDF, but the difference is that, so let's say for pregnancy. So pregnancies generally go 40 weeks. So at 37 weeks, there's a probability that the baby will be born. At 38 weeks, there'll be a probability that the baby will be born. At 39 weeks, there's a probability that the baby will be born. And they'll give it to you in a graph like this. But in reality, as you get further towards 40 weeks, the higher the probability is that your child will be born. So this one here is actually just a different, it's actually a different perspective of the probability distribution function. This is very important, and I'm only showing you this so whenever I use this word later, you guys will understand what I'm talking about. So to keep it moving along, let's talk about graphing, because when you have simulations, you need some kind of output, and I generally like to use graphs because people like to see graphs. So what do we graph? We graph trends. This is an interesting graph right here. This is a graph of the runtime in Ruby 1.93 of the simulation. So it's pretty constant. It goes up. You'll notice that as the iterations go, it goes up. And you'll notice towards the end that some of the dots don't appear to be on the line anymore. And what's happening there is we're actually running in the garbage collection. So every one of these dots that you see that is above is generally garbage collection. And can't configure when you really can't configure when Ruby's garbage collection is going to run. You can just make it run less. This is the same graph, but it's for JRuby. So you'll notice that, first of all, the slope of this line is way less. But you'll also notice something over here. Does anyone know what this is over here? Why this is happening if I'm using JRuby? It's hotspot. JRuby is actually, if you actually disable JRuby, it's really slow. Hotspot is actually being tuned right here. So actually, when hotspot becomes tuned, you'll notice that all those dots go away and that the slope is way less. So how do we create graphs like this? I didn't tell you this before, though, but if you're going to write simulations, you're going to have to know more than one language. One language you probably should know, just in general, is R. And I actually created that graph, these last two graphs, with R. Not very. And a good thing about R is it's very succinct. Once you get past this crazy arrow notation, you just realize that you're just building stuff and then plotting it to some kind of surface. Another thing you have to worry about is visualization. This right here is a DAG, directed select graph of the people and how they got their cooties. So person 1, they were patient 0. They had the cooties, and they touched a whole bunch of people. And this actually just shows how the cooties spread through the population. So the cool thing is that this graph was only created with this code. And actually, this is one of the outputs of a simulation. And it's made in GraphViz. So let's talk about how I built version 1 of this simulator. There was a loop. And every day there was a loop. And there was a bunch of people. And And what I did for all the people is I segmented them out, and I paired them. And there might be an unequal number of pairs, and then after they were paired, we determined if they shared cooties. And then pairs lasted of a certain amount of duration, and then it was over. So, like I said before, this wasn't fast. So for version 2.0, we wanted to think about how could we make this a little bit faster. So the first thing we have to realize is we need to be kind to MRI's garbage collector. One thing that I really noticed, and it was kind of awful, is that Ruby doesn't like whenever you have an array with, 500 million items in it. It just doesn't work very well. And even worse, Ruby does not like whenever you have an array with 500 million items in it and you want to insert in position 5. Really doesn't like that. So one other thing we have to think about is how can we make this run in more than one process? So we looked outside of MRI to start, and we said, hey, let's run this on JRuby. But here's a problem. JRuby is very compatible with Ruby, except when it isn't. And if you download JRuby today, I bet this bug is still in there. I hate to report it because it's actually, if I report this, I reported this to Charles Netter, and this is not negative against him. He says, put it in our tracker. But if I put it in the tracker, then I feel like I have to push it through the tracker. Rand with a range does not work in JRuby. It just doesn't work. But it works in Ruby 1.9.3. So it's not. There's always little incompatibilities that we found in JRuby. So we thought, should we just write it in another language entirely? Maybe we should. We did. But before I actually did that, though, we actually did write the simulator in Ruby for version 2. And before I did that, I actually want to start off with some benchmarks. What I'm benchmarking here is basically creating because here's one thing about Ruby that I was never sure about. I was never sure about how quickly can you insert into an array, how quickly can you retrieve from an array, and hash the same thing as a hash. So this is just right here, it's just testing out how quickly can I insert into a hash, and then, actually this is all this one's testing. So I noticed that big arrays, when I was running this under JRuby and MRI, I wanted to see what was the difference. JRuby always came out to be faster. JRuby just has faster data structures than MRI. But, something that everyone will tell you, micro benchmarks are not very important. They're very cool for showing that you are faster, but in reality, they don't reflect what might really be happening. So you notice, I included my prompt up here. You see the 3, that means I'm running an MRI. And notice that the third line from the end, the runtime was 129. The same exact code running in JRuby was actually slower. So be very careful of relying on your micro benchmarks because they do not reflect what might happen in reality. And I don't know the real reason why this is slower. I have some guesses, but that's not what we're going to talk about today. So let's talk about Rails won't scale. Actually, we're not talking about Rails won't scale today. We're talking about how Ruby won't scale. But that's also not true. We're talking about, and this is an important point that I want to make just in general, is that you can't say that X doesn't scale. What you're really talking about is my implementation of this idea doesn't scale. And we conceded the fact that this won't scale. So, not to give up, I actually went and read another math book and did more sciencey stuff. And I said, let me take another swipe at this. So, we have a group of people. You guys are really going to be good at this by the end. We have a group of people. We ask, person 1, are you ready to pair? We ask, person 2, are you ready to pair? We ask, person 3, are you ready to pair? And what we do with those responses is we put them on a priority queue. And you're probably going to say, Bryan, hey, we don't have priority queues in Ruby. I said, yeah, I know. Let's put it on an array for now. And we'll do it in insert. That's actually how I know that inserting into a 500 million array is very slow. And then what we do when we have a pairing, we ask the pair, will something happen? And then we ask the next pair, will something happen? And what we're trying to do is actually eliminate some of the iterations that we have to do. So here's just a little piece of math here that shows if we have 1,000 people and we have 636 pairs. Every single iteration, we have 1,636 choices. So I was thinking, well, how about instead of asking everybody if they have something to get done that iteration and asking every single pair if there's something that needs to happen that iteration, instead of doing a pull, why don't we do a push? So we came up with this idea of an event. An event class has really two basic methods. The event interface, there's no interfaces in Ruby, so I don't want to use those words, but the interface has two methods. You can schedule and you can run. So at the bottom, you can instantiate an event, you can run it, and you can schedule it. So what you can do is you can inherit from that, so we create a pair event. And then when we run, we add a person to the available pair pool, because we add a person to the available pair pool, or available to pair pool, and we don't schedule any other events. But if we have a contact, which means that, hey, I touched somebody next to me, we need to schedule the next contact as well. So, how do we keep track of events? Well, so here's where I was thinking of, why don't we just put it in an array? And every time we want to find an event, we'll just pop off the array. And I said, yeah, that doesn't quite work, because if I add to end of array, if I have event 1 and I want to have something happen in event 2 and I add to the end of the array, that's fine. But what if I want to have something that happens 50 events from now or 50 iterations from now? How do I do that? So I was like, well, yes, Ruby's array gives me an ability to insert at an arbitrary place. So I said, hold on, let me think about this for a second. I'm always running benchmark. So what is this? 1, 2 magnitudes of an order slower to do it this way? And I said, well, really can't do it this way. So I said, let me figure out. I said, Ruby has to have some kind of support for priority queues. So I actually went out and looked for priority queues, and come to find out that this gem called algorithms has implementations for priority queues, real heaps, and a whole bunch of other data structures you might want in Ruby. So I said, hey, I'll try this out. So same code that I showed you before is now that whenever we schedule our event, whenever we're ready to push events into our pool on the second line, we just say push the event at where we want to push it. And I'm going backwards here. So because the priority queue actually wants to work up, I'm actually working from the other direction. And this is, in the real world, is called discrete event simulation. And really what this is saying, so instead of having to iterate over every step, I iterate over interesting actions. But of course, there's always a problem. And back in the benchmark, and we thought that inserting was slow. This is a couple of orders of magnitude slower than that. So there is a compromise. There is a compromise in Ruby. To tell you the truth, when I first submitted this talk, our simulation ran in Ruby, and it ran slowly in Ruby. Then it ran in Clojure, and it ran not so slow in Clojure, but I didn't understand Clojure enough to make it really fast. And then I think it ran in Scala. I think there's a Haskell version, and now there's a Ruby version, which is extremely, extremely fast. It's actually over 10,000 times faster than the Ruby version. And that's only because I just really have great data structure support using discrete event simulations in Ruby. The cool thing is that I just make a very small Java process. I put it in a jar, and then I put it in a lib directory of a Rails app, and I can run it from there. So I wanted to say that where I'm leaving this now is that you can do really amazing things in Ruby. And if you is anyone here going to RubyConf? If you're going to RubyConf, you'll actually see how we can make this even faster in Ruby by actually injecting some C, maybe. So I don't know. So I want to thank you guys. I know that this was like really all over the place, but I want to show you that there's way more to Ruby than a lot of you. Who here is a web developer? See, you can still do Ruby outside of web and get paid very well for it. So I just wanted to show more people that this is possible, and that we are actually doing things in Ruby, but outside of the web development world, and we're really loving it, and I think other people will love it too. So thank you guys for inviting me, and you guys have been great. So I know I'm supposed to ask, are there any questions? I'm not really a scientist, so I might not be able to answer them. Yes?
Just know if this kind of stuff, experiments that you make, or are you using this kind of technologies in your real work or whatever it could be?
Oh, no, this is not made up. I've actually been spending most of this year writing simulations for large pharmaceuticals in the United States doing this stuff. So this is not hey, I wanted to make a presentation for a conference. Yeah, no, this is we really do this.
Okay, thanks.
With cookies?
No, unfortunately, we don't do cooties. We're actually doing more real-world stuff with different types of infections that cause cancer. So I'm not saying that I'm going to cure cancer because that'd be awfully pompous of me. But I will say that I will help somebody who might one day, with billions and billions of dollars of support, cure cancer. So I am actually curing cancer. So one last thing I want to leave you with is, and this is just a plea for a Rubyist to the rest of the world. People always say when you want to do scientific stuff, you want to do it in Python. And the reason they want to do it in Python is because you have such great math libraries in Python. In Ruby, we actually do. There's a gem called statistics. No, it's called distribution. And it actually uses a GNU GSL project, which is the GNU science library. And things like this will actually help us push Ruby forward and push us out of this web container. I mean, Rails and Ruby world is really awesome, and we've all really enjoyed it and made lots of money doing it. But there's just so many other things we can do programming and use Ruby. And I'm here trying to push it forward and try to use it in different places. So just to share with you guys today has been really fun. So thank you once again.